So one of the things I want to touch upon at the very end and just very briefly mention is heteronuclear diatomic molecules and ions. Um, when you have heteronuclear diatomics, that is, you have two different atoms that are bonding, the energy levels of the orbitals are not the same. And the reason for that is if you have more positive charge in the nucleus, that stabilizes the electrons, and those electrons will be further down in energy. So when we combine atomic orbitals, right, we only really ever combine orbitals of equal energy. When they're different, then we can only combine the orbitals whose energies are the same. And in reality, there's no good way to know when they're the same with just pictures like we're doing here. But I do want to get across the idea that molecular orbitals will be different energies, and the atom that has more charge in the nucleus, or as the book will put it, is higher electronegativity. That those electrons will be lower in energy than the one that has the lower electronegativity. Okay. In a sense, what that means then is when the two atoms combine, right, and one has higher electronegativity and one has lower electronegativity, the orbital energies will be closer to the atom that's most stable, and as a result, the electrons reside more closely to that atom, and this helps to explain polarity in bonds. So as I said, more electronegative atom is lower in energy. Lower energy atomic orbitals contribute more to the bonding molecular orbitals because they're more stable, so they make a bigger representation. And then the higher energy atomic orbitals will be higher in energy and contribute to the molecular antibonding molecular orbitals more. And then we also end up with something called non-bonding orbitals, where the electrons don't actually combine with the electrons with the other atom. They stay localized on the atom donating the atomic orbitals. So here's an example of a second period heteronuclear between nitrogen and oxygen to form NO. It's a radical. It's an odd electron species. The nitrogen and the oxygen, oxygen being lower in energy, both contribute 2 electrons to the 2s, the sigma 2s and the sigma 2s star orbitals. And then I have 3 from nitrogen here, and then I have 4 from oxygen here. So that's a total of 7. So I go 1, 2, 3, 4, 5, 6, 7. And then I can calculate a bond order for this. My bond order would be, I have 2, 4, 6, 8 bonding minus, and then 3 antibonding divided by 2, so I get a bond order of 2.5, like that. Now, because the bond order is 2.5, right, it's half. It's like between a double bond and a triple bond. And if you try drawing the Lewis structure of this, you end up doing something like this. You have N and O, so there's a total of 5 and 6, so I get 11 electrons. I end up with 2 for my skeletal electrons, so it leaves me with 9, and then I'll attribute the electrons first to the oxygen, and I end up with that. And then when I try to satisfy octets, I usually end up with something like this. So I've got 7 electrons over here, and I've got 8 electrons over here, and then the question is, what do I do with this 1 electron? Does it contribute to bonding or not contribute to bonding? And Lewis theory doesn't give us a good way to do anything with this electron. So the result is you can really only estimate that it has a bond order of 2, whereas in molecular orbital theory, it gives us a good way to calculate a bond order of 2.5 for NO molecules. So I wanted to show this one too. This is He2 plus. It's a relatively simple one, but we haven't talked much about ions. And first of all, we assume that He2 doesn't form, but it turns out He2 plus can form, and molecular orbital theory gives us a way to describe that. So for example, I have helium. I have 2 valence electrons, right? But He2 would have 4. So if I'm doing just He2, what I get is a sigma 1s and a sigma 1s star, and I can place 4 electrons in it. And when I look at this, I have as many bonding, so this is just for He2, I have as many bonding as antibonding, so my bond order will automatically be 0. On the other hand, if I do He2 plus, right, He2 plus will have 3 electrons. And so I can go 1, 2, 3, like this. And again, this is a sigma 1s, sigma 1s star. I get a bond order of 2 minus 1 over 2, or 1/2. So it turns out He2 plus is a stable diatomic ion that you can form in the gas phase. Now, what's weird about this one, and what's one of the reasons why I like pointing it out, it's very simple sort of to do this calculation to see a bond order of 1/2. What would the Lewis structure look like if you were to draw it for this, right? Because helium, if I were to bond it to helium like this, there's 2 electrons that are here. What do I do with the extra electron? Like in Lewis theory, this would be satisfied octets already, or duets. You know, the shell is filled with 2 electrons. This shell is filled with 2 electrons. But there's actually 3 electrons in this system. So what do you do with the one? Do you put it here, right? Do you put it like in between? And like I said, Lewis theory doesn't provide a good explanation. In molecular orbital theory, what we get is that that electron is in the antibonding orbital. So if we think about 2 helium atoms, oops, sorry, I accidentally stopped the presentation. This is the last slide. If you have 2 helium atoms bonded together, right, there's going to be a bonding molecular orbital that forms like this, which is going to merge, right? So I have He, He, that goes. And then superimposed on top of that, I have an antibonding orbital. So that would be something like this, and I'll do it in a different color. It would be on the outsides like this, with the node in the middle. And that antibonding electron sits in this orbital. It's not just in one side or the other. Remember, we're using quantum mechanics here, so the electron behaves like a wave, and the electron is just in this antibonding orbital, destabilizing the molecule. In He2 plus, what ends up happening, He2, sorry, what ends up happening is you put a second one in there, and there's as much destabilizing energy, and then these 2 atoms end up separating from each other rather than forming a stable bond between the 2 of them. So a simple molecule like this actually shows like the flexibility of molecular orbital theory, that I can just find these weird species, is what we would call them, and determine whether or not they're stable or not. And this is something that you wouldn't have been able to predict using Lewis theory or valence bond theory.